This is part 5 of the series Transformations. In the last part, we looked at the rotational rules for a rotation of 90 degrees counterclockwise about the origin. And we looked at the implications of doing multiple 90-degree rotations about the origin. Now, in this part, we're going to start out by working a couple of examples. Here we have triangle ABC. And we want to graph the triangle and its image after 4 separate rotations. We're going to be going counterclockwise about the origin. Doesn't say about the origin, but we're assuming so. Of 90 degrees, 180, 270, and then negative 90. First thing, let's plot the points. Point A is at 1, 3. 1, 3. Point B is at 1, 5. And point C is at 4, 4. And there is our triangle. Not too bad for freehand. Now we're going to generate the counterclockwise rotation 90 degrees about the origin. So remember, we're going to write the rule right here just so that we have it for reference. X, Y goes to negative y, x. And we started out with A, which is 1, 3, B, which is 1, 5, and C, which is 4, 4. Applying this rule, it's negative yx. So A prime is negative 3, 1. B prime is negative 5, 1, and C prime is negative 4, 4. Notice we're taking the y coordinate, it becomes the x, and it goes negative. So this is negative y, x, x, negative y, x, negative y, x. So our new points are negative 3, 1, negative 5, 1, and negative 4, 4. And this is a 90-degree rotation. Now, if we were to draw through any two sets of points, let's take 1, 3, this is A, and negative 3, 1, this is A prime. And let's go ahead and draw an angle. So we'll draw two segments, one from A prime to the center of rotation, and one from A to the center of rotation. And you can see that it's kind of rough there, but it forms pretty close to a 90-degree angle there, which indicates that this point has been rotated along the circumference of a circle centered at the origin. All right, let's continue on. We're going to take these points now, and we're going to apply this transformation rule to get a 180-degree rotation. So let's go back to our white. And a double prime then is going to be negative y, x. And B double prime, negative y, x. And C double prime, negative y, x. So this was 90 degrees. This is now 180 degrees. And let's plot the points. We have negative 1, negative 3. We have negative 1, negative 5, and negative 4, negative 4. And there is our third triangle. And this is A, so it says negative 1, so this is A double prime, which is negative 1, negative 3. And if we were to draw another segment from the origin, we would see pretty much that forms a straight angle in there. And that's our 180 degree rotation. Now one last rotation. Let's do our 270. So for 270, our A triple prime is going to be negative y x, and B triple prime is negative y x, and C triple prime is negative y x. And let's plot those points. We have 3, negative 1, 5, negative 1, and 4, negative 4. I forgot to draw on that line. And one final time, let's draw in a segment here from the center of rotation to our A point. And you can see we have another straight angle. 90 degrees, 90 degrees, 90 degrees, 90 degrees. So that is counterclockwise rotations in increments of 90 degrees. And obviously this point was A triple prime. Okay. Now, you can see fairly clearly at this point that if we were to take this pre-image and rotate it clockwise 90 degrees, we would be going in this direction. And so this figure would end up at that figure. So if you want to do a 90 degree clockwise rotation, it's the same as 270 counterclockwise. 90, 180, 270. So that's all you have to know is this one rule. All right, let's move on and work another example. In this example, we're going to be doing a composition of transformations. The first transformation is going to be a translation, and we're going 2 in the x direction and negative 1 in the y direction. And then we're going to do a rotation of 90 degrees about the origin counterclockwise. And we're going to start with segment DE. First thing, let's go ahead and write down our points. So we have D, which is at 2, 2, and E is at 6, 3. So the translation, D prime, is adding 2 to the x, so 2 plus 2 is 4, subtracting 1 from the y. 2 minus 1 is 1. E prime, adding 2 to the x, that's 8, subtracting 1 from the y, that's 2. Now if you want, we could draw the intermediate figure, or we could just go straight for the final and draw the image once. So that's what we're going to do. D prime. Now remember, we're using the second image here. This is our pre-image, and we're going to now rotate this set of points. So we're taking 4, 1 and 8, 2 and applying the 90 degree rotation rule. Hopefully you remember it. And let's write it. X, Y goes to negative Y, X. So D prime, negative Y, X, negative Y, X, and E double prime, that was D double prime, negative Y, which is negative 2, X, 8. So this is our pre-image, this is our image. Now I can just go ahead and write it. Negative 1, 4, and negative 2, 8. and this is D double prime, and this is E double prime. And that is our new segment. And just for kicks, we can go ahead and write this translation. This is 4-1 and 8-2. So this was our translated point. And I'm going to show the rotation here. So let's draw a segment from here to the center of rotation, and a segment from here to the center of rotation. And you can see that that looks like pretty close to a 90-degree angle. So that is a very simple composition of transformations. And this is also a rigid motion because both of these transformations were a rigid motion. So the translation is a rigid motion and the rotation is also a rigid motion. So the composition was a rigid motion as well. Now we're going to take a look at, now that we've looked at rotations, we're going to go back to the concept of symmetry and look at rotational symmetry. The idea of rotational symmetry is just as it sounds. An object has rotational symmetry if it can be mapped onto itself by a rotation of 180 degrees or less about a central point that is called the center of symmetry. Now, up to this point, we've done rotations where the point is outside the object. In our case, it was the origin. In this case, the point of rotation around which we're going to rotate all the points is the center. You can think of it as the center of mass, but it's the center of symmetry of the object. We're not going to worry at this particular juncture how to find that center of symmetry. But if we can take this triangle and rotate it through 180 degrees or less and map that triangle onto itself, then it has rotational symmetry. And more formally, the center of symmetry is a point around which an object in a plane can be rotated to map the object onto itself. All right, let's take a look at some dynamic examples of objects that have rotational symmetry. Here we have a square, and this is our center of rotation. We're going to go ahead and start rotating this object counterclockwise about the center of rotation. And you see if we rotate it 90 degrees, it's mapped onto itself. So this object is said to have 90-degree rotational symmetry. If we keep going and go to 180 degrees, it maps onto itself again. So this object has 90-degree and 180-degree rotational symmetry. That's a square. Now let's take a look at a triangle. A triangle. Let's start rotating this triangle. This is its center of symmetry. We rotate it, rotate it, rotate it. In this case, we have to rotate it 120 degrees to get it to map onto itself. But this figure has rotational symmetry. It has 120-degree rotational symmetry. If we keep on going to 180, we don't map onto ourselves here. So this figure only has 120-degree rotational symmetry. Now, let's try a hexagon. Here's the hexagon. Let's start rotating it. We rotate it 60 degrees. It has rotational symmetry. 120 and 180. So a hexagon, these are all regular polygons, it has 180 degree, 120 degree, and 60 degree rotational symmetry. So that just gives you an idea of how different objects can have different types of rotational symmetry. Now we're going to go back and look at a couple of basic examples. In this example, we want to determine if these objects have rotational symmetry. This one does. It can be rotated 180 degrees and mapped onto itself. This one is a square, so it does. It has 90 and 180 degree rotational symmetry. This one does not. Even if it's rotated 180 degrees, the arrow would be pointing that way, would not map onto itself. That is rotational symmetry, and that wraps up this part. I will talk to you in the next part.